today. First one would be the Vast.ai. Now, what Vast.ai is one of the place at which we host our instances. So Vast.ai offers us competitive prices as compared to the AWS or the Azure. So this is where our servers lie, and this is one of the machines that I rented just this morning. It has about 64 GBs of virtual RAM and 16 GB of virtual cores along with the 12 GBs of GRAM, the graphical RAM. And this is where we'll be connecting into. So we can just directly get into a Jupyter instance over here. Now, this is one of the stuff that I'll be walking through, and this is the LSTM presentation. So the first thing that we'll do is connect to the instance over here, and we'll be running few of the codes that we have already laid down over here. So first of all, we'll have to SSH into our server. So for that, they have provided us pretty basic functions over here. We can just directly copy paste this command into one of the terminals. So for example, this is our terminal and we can just directly copy paste our code over here, and it will ask us for the confirmation of the key print. And once we have the confirmation, we can just directly get into the machine. Now once we are into the machine, we can get into the home directory. Over here I have already created one folder named Perceptive Analytics, and in here I have added up the codes. So over here, first of all, we'll have to download the data set. To download the data set, we'll have to run few of the commands which I had added over here. First one would be the installation of Fast.ai. Now this installation will take a while. So in the meanwhile, we'll just let this process run in the background and we'll get through the LSTM presentation. Now LSTM, as you might be knowing that there were a couple of changes which were made in the industry in the large language model segment in past couple of years. First one was the transformation from RNNs to LSTMs, and second one was the transformation from LSTM to the transformers. So we'll get into why LSTM is used and why not RNNs are used as of few years ago. So for example, this is just two sentences that we have over here. First one is that today, due to my financial conditions, and we need to predict the next word. And in other word, we are trying to,
Harmit,
yeah,
one quick request here. Can you
yes, yes.
just help everyone know what are RNNs and what is LSTM?
Oh, yes, yes, yeah. Okay, sure. So RNNs are recurrent neural networks. It is just a series of neural networks. And in it, the as compared to the traditional neural networks, there is one of the feedback layer which is passed within the model itself. And this feedback layer tries to help the model remember what output was predicted a couple of words before the current word is encountered. So model tries to remember the thing that it had predicted. It can be used for forecasting and for example, forecasting in terms of weather forecasting or the stock prices predictions. And LSTM also works on the similar note as compared to that, but it has the option to modify its hidden states. It can also selectively learn something and it can selectively forget something. So that is how LSTM and RNNs are a bit different. In
Yeah,
LSTM as
the
well,
full form of LSTM.
yes, 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 LSTM. The full form of LSTM is long short-term memory, and RNN is recurrent neural networks. So these are two different things, and LSTM internally also LSTM uses the neural networks itself as its internal implementation. So these are two couple of sentences in which the length of the sentence is pretty small. And when the length of the sentence is small, at that time we can work with RNNs. So for example, when this is the sentence, today due to each of the individual words would be passed through the model one at a time. These are different layers within the model. And when a different word is passed, at that time the model would try to learn some weights, and these orange dots, those are the weights, and these blue colored arrow, that is the feedback. That is the feedback, and that is the hidden state within the model, which tries to remember something and tries to carry down the model. I'll just get to that. So for example, over here, this is one of the word today, and on the basis of that, the next word, which is the need, is predicted. This is how RNNs work. And when we zoom down into one single node over here, when one single word is passed, at that time we can see that where there is one short-term memory which is within the RNN, but there is no long-term memory. So this long-term memory is not present. But if we would have had something called long-term memory, at that time the model would have been able to remember much more efficiently. So that's where we get into the LSTM segment. So keep a hold of this. We'll get into this in detail.
Yeah.
So
Can we
right
just
now,
so each of the dots is a neural network, is it?
yes, exactly. So
And yeah, go ahead.
each of the dots is itself a layer within the model. And so what happens is typically our model goes from left to the right, and we have input over here and the output over here. But in our case, it is a time. So when the first word would be passed, it would be passed through the entire model. This is the input of the model. This is the output. And in the model itself, there is a hidden layer which is stored within the model itself. And this hidden state is passed down to the model, and model remembers what was predicted before a few words. So I hope this is making sense that yellow dots are itself the layers within our neural network. So this is how the RNN has its basic architecture, and this is how we are planning to add something called as long-term memory within the model, so that we know something that needs to be remembered in the model in the longer run. And for example, over here, the T3 is the third word. The third word in this sentence, the in this sentence, and that Q, when that is passed within the model, this XT would be the tokens. You can understand of tokens as if like numbers. You can assume this as a number and this as a hidden state. Now these two things would be coming into the play, and individual weights would be assigned to these of the numerical matrices, and those would be multiplied. It would be weighted sum average over here as suggested over here, and then after a new hidden state would be formed, and this hidden state would be passed down the model. So this is the computation which happens inside each and every different node in the neural network. So whenever different word is passed, this computation would happen, and the hidden state would be modified at each place. So this is how it goes. But as we were discussing that we are planning to add one hidden state as well. So this is no, sorry, the long-term memory state. This is the hidden state. We'll be adding one long-term memory state as well. So this CT minus one, that would be the long-term memory. This would be the stuff that would be remembered by the model. So this is where the LSTM comes into the play. For example, this is one sentence that Dhaval eats samosa every day, and we can guess pretty easily that his favorite cuisine would be Indian. But over here, Dhaval is talking about himself and his brother Bhavin as well, and where Bhavin loves pastas and cheese. But over here, when the model would be asked to predict the next word, the model should be able to predict Italian as compared to the Indian, which was in the earlier case. So RNN would pretty much be successful over here, but RNN fails dramatically at the cases where the sentence length is increased to a few folds. So this is what would happen when if we were able to just working on the RNN. At that time, the model would be trying to remember some stuff, and it would be trying to use that particular keyword. For example, if it is movie review, it would be trying to predict it if it is positive or negative based on some certain keywords, like it was movie was awesome or movie was beautiful or something like that. So likewise over here, the model would be trying to remember the stuff that will come into the play. For the first two words, there is nothing significant to remember, but over here the model would be remembering samosa. But after that, when the pasta and cheese would come into the play, the model should remember them and delete the samosa part. This is what is not happening inside this is not happening inside the usual one, which is the RNNs. And likewise over here, we'll be able to predict Italian if pasta and cheese is stored. So this is what the three different gates of LSTM come into the play. The first one is the forget gate, which is we need to forget this samosa over here and replace it with pasta. So this is the internal architecture of a single LSTM cell. Likewise, we were discussing over here, we're looking into the single cell of RNN. Over here, we are looking into a single cell of LSTM. So over here, a particular word will come and the hidden state, and then after those weighted averages would be happening along with their weights, and the sigmoid activation function would print the output within 0 or 1. If it is 0, the memory of the samosa would be modified, because when it is 0, the multiplication of this earlier memory state and the sigmoid activation would be 0. If the sigmoid is outputting 0, at that time the forget gate would be opened and the earlier state would be forgetted. On the other hand, if it is 1, at that time the memory of samosa, which is the earlier hidden state, that would be retained. Likewise, we have forget gate. The second gate that we have is input gate. When we want to store something new inside the mod. For example, over here, when we were at pasta, we had to save pasta and forget samosa. So forget gate forgot the samosa, but the pasta that would be done by the input gate over here. So when pasta would be coming into the plate, two of the activation functions would be used. One is sigmoid and second is tan hyperbolic. And those weighted averages would be computed. Multiplication would happen at the input gate, and then after the same hidden state which was trying to remember the earlier long term state, that would be modified, and here the memory of pasta would be added. So this is how the input gate would be coming into the play. But as we know, this is a long term memory, and over here is a short term memory which we still need to edit. So this is where the output gate would be the coming into the play. So this long-term state would memory would be working differently, um, and this hidden state that would be computed based on the word that we have and the hidden state. Along with that, again a sigmoid activation function would be used, and then after the output would be computed based on the current word, and along with it the input gate which we had just previously used. And hyperbolic activation function would come into the play, and we'll have a hidden state over here. Now if you are working on named entity recognition, at that time the yt would be important, but since our task is just for the prediction of next word, yt could be completely ignored over here. So this is how the entire LSTM architecture works. And I have not talked into any mathematical stuff, but I have added one reference over here which tries to talk in terms of the mathematical formulae, and this is pretty interesting. Just the same thing that I talked about. This is the hidden gate. This is the input gate, and this is the output gate. All of those three gates are talked in terms of mathematical sense over here. So this is also one of the interesting reference that you can look into. So this was all about LSM. Now we can head back to our model, see how our model has completed task. So it ran the first one of the command that we did give. Now we'll just install a couple of different libraries as well. We'll just install this one. We'll install Kaggle one as well. Then we'll just update it and upgrade it. Yes, this one is being done so that we can install unzip. Unzip is a usual command which is used for unzipping the zip files. Okay, this is done. Now what we'll be doing is that we have one API key of Kaggle. So what Kaggle would be used so that we can download the dataset. We also have downloaded the made our own custom datasets. Those datasets are present directly over here. You can see that kaggle.json API. We'll just quickly make a few folders and transfer our file to the required location. This is done, and we'll just do this one. We'll just change the permissions for the newly obtained Kaggle file. Now, after that, we'll be able to directly communicate with Kaggle through our terminal itself, and we can see different data sets that we have present. Now, we'll download the data set. For that, we'll have to get into the dataset tab, and over here, we have this pretend folder. Over here, we'll download our dataset. This is where our dataset lies, and we'll just run this command and the dataset would be downloaded. It will take pretty much just a few seconds. They have pretty great bandwidth as for sure. And now we'll just directly unzip this file. Uh, Unzipping this file, we'll just save it directly over here. And all of the 42,000 Telugu dataset files that we have present, those would be unzipped directly over here. This would take just a few seconds, and all of those files are unzipped. Now we do have to clean up. For that, we have a cleanup.py file which we have also made. We can just directly run this command, and all of our files would be cleaned up as well. So the cleanup has not happened. We'll just look into that. So this is where our cleanup.py file exists. And over here, we'll just copy our location, and now it should be good to go. So now the pre-processing of each of the 42,000 files is happening right now. And after that, we'll be just uh, running one script which would do all of the running of the model. So this is the script that we have already made. And using this script, this is where
So, Dharmik, in cleanup, that's a custom file that you had created, so that it can you can clean up some of the pieces, or what exactly is happening in cleanup?
yes. So in the cleanup, basically we are trying to remove English characters we are facing. Along
Okay,
with that, any HTML tags or any square braces. And
got it.
this is where we are removing the tags and just removing few of the specific characters that we are encountering. So this
Okay,
is just to make sure that we only have punctuation marks like question marks and exclamatory and full stops. That is our main motive over here. And
okay.
uh, yeah, and I think the cleanup is also done. And this is the actual model. This is our model. Over here we have a couple of codes in the model architecture. I'll just add details to those codes uh, in one Notion page and share it in our channel. Now the thing is that over here, this is where our model would be stored. So we'll have to change this path because this was on my local system. But right now we are on the server. So I will have to just change these paths over here. We'll quickly do that. Yes, this is the path where our model would be where we'll be storing our model. So I'll just copy this path over here and paste it directly into our model directory over here. And this one would be the input path, which would be used for the data set, which we just had over here. I'll copy this path as well, and I will paste it directly over here. And over here, the docs. Yes. No, we don't need to do the docs because we have done it on the line number 2038. Yes, so this is the only change that we need to make, and the rest of the stuff would be staying the same. For example, currently we will just be working with learning rate of 0.01. Epochs would be just 10, and the number of unfreezed epochs which would be used for checking the optimal learning rate, that would be just kept one as of now. And we can just try to run this file. I'm not pretty sure if we will be able to run this because we have not made any more changes, and usually errors are faced whenever we try to run these files. So we'll just see what is happening over here, and we have our codes over here, and we'll just have to run this script. And it seems everything is going good. So these are just couple of paths that we have. There is one sentence-based model which would be used for the tokenizing of the entire document that we have. What tokenizing to does, it tries to break individual words. So you can understand it like a space tokenizer in which each of the words are separated based on the space that we have. So whenever space would be encountered, at that time the two words on the left and the right would be stored into different tokenizers. And after those tokenizers, we can get into the vectorization of those numbers. So what vectorization would do, that it would be trying to convert the words into numbers and try to find similarity between words. For example, let's say a boy and a girl. So boy and girl should have the vectors identical because they account to something similar stuff. Likewise, cat and dog because those are animals. So that is where the SPM would be done. There would be one SPM path that would be generated, the model where model would be stored, and the vocabulary file where the vocab file would be stored. So vocab file is the number of different words that we have. For example, in our case, if I'm not wrong, we have about yes, we have kept our vocabulary size as 1,20,000 over here. So what 1,20,000 is that when we have a cat and dog classifier, we are trying to predict either one of the two. Likewise, in our case, we'll be trying to predict one out of 1,20,000 words, and that would be what would be coming as our next word into our model. So this is all that would be happening over here. I'll just add these details to these codes and make a Notion page and share it within our group. And all of these things are good. This is just where the prediction of the model would be happening, and further details could be found in this one at which the architecture of the model is defined. And internal implementation is not the LSTM, rather the internal implementation is EWD LSTM, in which we try to drop out few of the nodes so as to prevent regularization, so as to prevent overfitting and to enhance the regularization. So this is all would be happening over here. And once our data loader would be um, finished with over here, the model training would actually begin. But I'm sure the model would I was expecting it to fail right now because we have currently right now 12 GB of RAM. I'll just quickly show that. So this is where our model is. This is where our instance is, and this is our current model, current details of the model. Like we can see over here, currently just 0.2 out of the 12. Okay, now we are using 3 GBs of RAM over here and just 4 GBs of the GPU. And along with that, we can just SSH here into one of the terminal and just see the utilization of the NVIDIA chip that we have. And that would provide us much more details into the amount of the RAM that is actually being used. It will just take a bit. Okay, we can just run one command and we can just directly check the amount of GPU that we are using. So we are currently using just about 3 GB of GPU out of the 4 GB that we have. So it's pretty good. We can change the batch size. So for now we are working on batch size of I think 64 if I'm not wrong. Uh, no, the batch size was 128. So it's pretty good. We can go for batch size of 256. But possibly the model can crash in that case when it tries to allocate more memory as compared to the actual allocation that is possible right now. So this will go good for now, and it should take about 7 minutes over here, and such Dynapux so it would complete the training in 70 minutes. So this is just the pre-training part, and after that fine tuning would be done on the model. Yeah, and we have disconnected with the server. And if we want, we can also stop our server over here. So when we are not using it, we can just directly pause it so that we do not incur any additional cost. And also the pricing is pretty low. Like we can see over here that our per month cost over here would be about $53 if we are working over here. This which is pretty low as compared to the AWS and Azure as well. So thanks a lot. This is what I wanted to discuss today.
Okay, any questions for Dharmik?
Dharmik, in the LSTM architecture, I actually wanted to know like there were some functions, sigmoid and hyperbolic tangent functions. So like I understood the by sigmoid function is used, but what is the significance of hyperbolic tangent function there? Mainly.
Yes, so what hyperbolic tangent would be doing is that it would be like sigmoid is giving us output from 0 to 1. The
Hmm.
hyperbolic is giving us output from -1 to 1. So at that time, when we want to store some different information instead of forgetting, for forgetting, we can just work with 0 and 1. If it is 0, we'll be forgetting. If it is 1, we'll be retaining it. If at the other hand, in the input gate, we'll be using hyperbolic, we can use -1 to actually make the changes over the value over there itself. So if it is -1, all of the matrices values would be inverse at that time. And we
Okay.
can just directly get a new value from that itself. So that is why tan hyperbolic is used at that place. And also it can also work with zeros as well.
Okay. Thank you, Dharmik.